Okay, so we're going to continue with the reading. We're going to start here on November. So, on November 16, 2017, the American Chemical Society hosted a webinar featuring Dr. Wendy A. Ware taking a look at technological advances that have significantly changed chemical research, as well as what the future might hold. She pointed out that environmental and ethical chemists now also have an option of cloud computing, instead of hosting computational power in-house. In this sense, the cloud allows smaller organizations that do not have information technology departments to compute using online tools. There is also an interesting review on the state of the art related to the feasibility of making sensing devices, for instance those utilized in environmental analysis, ambiguous, flexible, and comfortable to any object of surface, since it will also allow them to become part of the core of the IoT revolution, which demands system mobility and self-powering functionalities to meet the requirements of most environmental analytical chemists. On the other hand, the fact that IoT devices are frequent targets of attack makes security a critical issue. Nevertheless, care must be taken when addressing it, since there should always be a compromise between security demands and ease of assembly, use, and maintenance. In this sense, Chamberlain et al. Describes industrial deployment experience on the iZeta Connect security infrastructure implemented by Beps Technology, Inc., a company specialized in water chemistry monitoring. NO2, along with other nitrogen oxides, interact with water, oxygen, and other chemicals in the atmosphere to form acid rain. That is why its continuous monitoring is of capital importance in environmental analysis. For this purpose, a three-dimensional area, a high specific surface area, superhydroponic, reduced graphene oxide with unique interactive structures was synthesized by plasma sintering in one step of highly selective NO2 detection. The resulting sensor demonstrated the practical capability to detect 50 micrograms liters minus 1 NO2 with a very low theoretical limit of detection of 9.1 micrograms liter minus 1. The good tolerance to environmental changes such as humidity and temperature makes the sensor suitable for reliable application in IoT under ambient conditions. Unfortunately, this paper does not contribute to the IO research. Only a lab-built software is detailed to control the sensor, but nothing about IO protocols or communications issues are detailed. As a part of environmental pollution monitoring, there is a growing need to autonomous sensors for untainted continuous nutrient monitoring in water. Both institutions and industries require frequent water quality control, but is usually time-consuming and expensive. Autonomous sensors permit frequent and attendant data collection, although sometimes at an unreasonable prices. That is why the development of low-cost sensors is essential to realize the concept of IoT. Nevertheless, much work still needs to be done in this field. Guy and Regan they have reviewed the current literature on the research and development of a tunable autonomous sensor for PO4-3 and NO3-. Out of this being put on analytical performance and cost. Furthermore, some recent sensing approaches that could be automated in the short to medium term are included, along with an overview of approaches to the monitoring of road animals. They are compared with standard laboratory procedures as well as with commercially available sensors. For both inorganic species, the role of sensor network in decision-making is also discussed. From IoT perspective, this paper only highlights the necessity of low-cost sensors. Without low-cost sensor, IoT deployments would be possible. Additionally, authors identify wireless sensor networks as a basic technology for the success of IoT. Unfortunately, nothing about IoT research is accomplished by the authors. There is an increasing research interested in chemo-resistive gas sensors based on two-dimensional material, including graphene-based material, mainly due to their potential use in new technologies such as IoT. Major features of this sensor are high selectivity and reversible response and recovery. In this sense, an easy solution process that recently been proposed, the resulting chemically fluorinated graphene oxide sensors developed show improved sensitivity, selectivity, and reversibility upon exposure to NH3 with a really low theoretical detection limit of 6 micrograms per -1 at room temperature. The author points out that the remarkable NY3 sensing properties offered by this type of sensor and research by first principle calculation will enlarge the possibility of functionalized 2D materials for practical gas sensing applications, such as IoT. From this perspective, this paper doesn't make any contribution in IoT technology. Simultaneous progress in chemical sensing and wireless communication technologies has given rise to the development of wireless chemical sensors. These hybrid devices enable wireless determination, collection and distribution of chemical analytical information in a way that it is significantly impacting the sensor of IoT, with application in environment and other fields. Challenges and examples for each of the major chemical sensors and major radar technologies related to different applications areas are reviewed over the period 2007 to 2017, including the latest trends emerging from wearable sensors. Special attention is paid to radio bases (WCS), showing that ubiquitous wireless technologies such as Bluetooth, Zigbee, radio frequency identification, and near-field communication clearly contribute to make analytical chemical sensing suitable and realistic for market needs, especially for electrochemical and optical sensors. Although this paper shows in a deep review of existing wireless chemical sensors, it does not include the most actual and promising IoT protocols such as 6 LoRa. Modern IoT proposals for the environmental chemical solution must include an in-depth study and consider the use of these protocols. Recent solutions use wireless technologies from a few years ago based on wireless sensor networks and gateways or SIMs to upload data to Internet. Most solutions only upload data to Internet, but do not offer real IoT solutions of accessing data. Wireless chemical sensors are increasingly important in environmental analysis as well as in the rapidly emerging area of the sensor IoT. In such wireless scenarios, the application of fluorescence-based sensor is lagging behind other types of transduction mechanisms that would allow development a new low-cost and highly portable wireless fluorimeter for optical chemical fluorescence intensity measurements. It has been a major step forward since fluorescence-based sensors are not so frequently used in wireless sensors networks. These devices then program and communicate wirelessly with mobile devices or personal computers by either radio frequency identification or near-field communication. It is easily adaptable for utilization with different fluorescence sensors, chemistries, and analysis. Its highly versatile fluorimeter has been successfully tested in the laboratory by means of different assays with fluorescein and paper immobilized kinase sulfate fluorescence indicator. The author then concluded that their system could significantly contribute to some emerging areas of mobile chemical sensor research, including the sensor IoT. Unfortunately, the presented solution cannot be classified as an IoT application as only connect the chemical sensor via RFID or NFC to a mobile device that is connected to Internet. It is commonly accepted that a quiet culture of oysters represents a major source of income in some coastal areas. Nevertheless, the ground rate of oysters heavily depends on several environmental parameters, such as temperature, salinity, turbidity, pH, and dissolved oxygen. In this sense, Viegas and co-workers have proposed a cloud-based platform to obtain the values of water quality parameters that affect Oyer's ground. The paper describes in detail the hardware and software of the measurement system, as well as the storage and processing of the obtained data. It also concludes several experimental results about the aforementioned parameter. This solution is a real cloud-based platform that uses the 4G cellular network technology to communicate information. It uses the ThinkSpeak platform, an IoT analytics platform service that allows the aggregation, visualization, and analysis of data streams in the cloud. The real-time monitoring of water quality in real time has always been of great importance for researchers and regulatory agencies worldwide. A typical method consists of employing the sensor network in a setting of IoT to detect and measure water quality parameters and share the resulting data by means of the Internet. Bear that in mind, sensitivity and salinity sensors based on interdigitated microelectrode array (IDA) electrodes have been developed for the detection of residual chlorine in the form of hypochlorite ion (IDA) sensor with an ion sensitivity could show higher sensitivity and about 600 mV with HCl O- liter increasing from 0 to 10 micrograms difference, liter minus 1, more than the additional sensing method. Both the response mechanism and selectivity have been dealt with. Furthermore, several materials components that affect the sensing process were tested. On the other hand, the stability, repeatability, and linearity have been significantly improved. The authors claim that micro-IDA chips with improved ICs in membrane show a strong potential of research chlorine detection for application with water monitoring. But it is not limited to these species, since they also show high selectivity to other common ions in water such as sulfate, carbonate, and chloride. Other advantages also include small size, low cost, rapid response, and low power consumption, which is particularly suitable for iron. Nevertheless, further details regarding reliability and standardization are missing in this paper. It is often believed that environment analysis still has to take full advantage of the benefit of low-cost data gathering by IoT sensors. In a sense, however, a recent work has focused on some hands-on experience of using those IoT sensor devices in environments. Additionally, this research contributes to lower computing costs by integrating edge and cloud computers in the process of data gathering. Ultimately, it also means a reduction in the global cost of the distributed IoT sensor network. Or reshaped and his team analyze the process of integrating chemical and liquid gas detecting sensors into the IoT, using recently developed sensors that are integrated into wireless platforms. As a starting point, a microfluidic sensor to detect different types of liquid is presented, along with gas sensors that are able to signal the presence of target gases in really small amounts. These species include dimethyl, methyl, propanate, total, ethyl, propanate, and ammonia. The optimization of data transmission is one of the key points in the success of the application of IoT technology. Environmental analysis. For this purpose, several compression techniques have been explored. One of them, compressive sensing, is a really attractive model to be incorporated in the development of IoT platforms. Compressive sensing is a signal acquisition and compression theory that benefits from the outsider behavior of most natural signal and IoT architectures to obtain power-efficient, real-time platforms that can lead to interesting IoT applications. A recent comprehensive review has dealt with the incorporation of CS and IoT applications with the help of existing bibliography. Furthermore, the author remarks some major emerging trends in future CS-based IoT research. Another interesting review covering the period 2013-2018 critically discusses biosensor and chemosensor technologies and concepts utilized in an IoT setting are considered IoT fit. The authors select these analytical chemical devices due to their ability to be remotely located, their adaptability to the dynamic of the environment, and the fact that they easily function in networks, very important in case of continuous monitoring of environmental parameters. Besides, as the author highlights, they have made the greatest progress towards IoT integration. The paper is completed with a revision of present and future challenges, regarding affluent duration into a global analytical concept. Capella et al. Have recently proposed a new approach for the development of better sensor based on cloud services and IoT. Their proposal has been applied to the development of a potentiometric sensor for determination of bicarbonate in water. The data obtained by this sensor are updated to the cloud so that any user can access them. Furthermore, in taking advantage of the sensor connection to the network, this device makes use of the information available in the cloud, mainly pH values, which leads to a virtual carbonate smart sensor with a better performance, lower cost and energy consumption. From a chemical point of view, the results obtained were straightforward with a highly satisfactory accuracy and precision. A computer experimentation was performed to compare the proposed device with other classical sensors. Moreover, the author points out that this work allows for the implementation of a new generation of smart sensors and, at the same time, joins the recent IoT waves. In this sense, it must be borne in mind that IoT proposes to decouple information sources and consumer in such a way that any application or device may use information provided by other environments, and information generated by any application or device is available for others. Finally, Munoz et al., coinciding with the conclusion, shows in present the development of an IoT-based water management architecture to be applied in our industrial district. This proposal concludes desalination plants, connection to the public utility network, and several consumer items. They provide a detailed description of the design of an IT environment to carry out the optimal management of the heterogeneous resources required by the elements that make up this environment. And in spite of the fact that only simulation results are presented, their approach demonstrates the benefits of both the need for a coordinated research between the IoT techniques and environmental analytical chemistry. Although only a few approaches really integrate IoT in a global way into an applicable IoT solution. Research groups specialized in environmental analytical chemistry provide sensors that are increasingly suitable for this environment, whereas ICT-oriented groups devote themselves to improving infrastructure and supporting the cloud. Nevertheless, we miss a real effective symbiosis between both fields that allow the development of interior efficient solutions with a view to achieving optimum standardized advances in this line. It is then important that the new proposals are based on consolidated IoT platforms so that previous contributions from other groups may be utilized. 4. Conclusions and future trends. In previous sections, IoT environments and their contributions have been commented. Now it is a turn to critically discuss benefits of IoT in cloud and environmental analytical chemistry, and what this discipline may offer to those technologies, taking the need of migration from the laboratories to the real environment as a starting point. We believe that this symbiosis is very important, supported by the development of low-size and expensive and low consumption sensors that are able to work and still based on energy harnessing technology. What advantages may environmental analytical chemistry obtain from IoT? The starting point is the aforementioned Gartner's report, according to which in 2020, 95% of newly designed electronic products will be equipped with IoT technology. This means that chemical analysis instruments will be developed to integrate themselves into IoT ecosystem that will be hosted in the cloud. It will then be necessary to equip laboratories with the required communication infrastructure. Thanks to the ability in the cloud of this huge amount of data, new perspectives will be opened up in many fields of environmental analytical chemistry. In the near future, trends show the possibility of obtaining nearly any measured data, regardless of its source, on a common platform and accessible for any application, being public or private, and examine the manufacturers of sensing devices to be able to know in real time how their products are working, which will lead to the development and implementation of better sensors and trained users. On the other hand, the information on the environment where devices working will be immediately available, thus allowing for the sustainability of the sensor to the environment as well as implementation of devices with extreme working limits. At a given moment, any device or user in a cloud will be able to consult and utilize this information for his/her own benefit. In this sense, the approach is considering the information in the cloud as a neutral sensor consulted rather than obtained measurements are extraordinarily interesting, since they permit supplementary functionality of real sensors. Thanks to this virtual sensor, it is then possible to apply redundancy techniques, fault tolerance, or interference rejection without incorporating new devices, no extra cost. As an example, our research group is now working on the determination of bicarbonate concentration in aqueous media using classical CO2 sensor. Additional information required pH being obtained from the cloud whereas the obtained concentration values are stored in the cloud. The integration in the cloud will allow for the evolution of the all-modern wireless sensor networks, according to which a set of predetermined nodes monitor a parameter in a continuous way. Engineer collaborative sensorization networks where heterogeneous sensors with different purposes integrate their measurements into a common IoT platform. In this sense, even denser networks could be created, for example, by integrating this sensor into a smartphone of laboratory person. This information as a whole could also be offered to provide new devices. Initiatives such as open data from New York City or Valencia, our hometown in Spain, already gather and offer a great amount of data, but from whole domain or provided by private agents. IoT ecosystem generate a great amount of data. Those treatments can only be dealt with through cloud computing, with high scalability makes the resources nearly unlimited. Significant advances have taken place in the field of data science. Gartner forecasts that by 2020, more than 40% of data science tasks will be automated. That is why that environmental analytical chemistry cannot ignore the impact of these new techniques in scientific research. What benefits who bring environmental analytical chemistry to IoT and cloud computing? Although Internet of Things is going to become an intelligent environment capable of interacting one-on-one with a human being in its senses, taking into account that a computer vision and image processing and in some way the sensor side of IoT and the personal assistant can be considered as the Earth's environmental analytical chemistry is destined to become IoT's and smell. In global terms, there is no doubt that it will be necessary to provide data for the IoT when it addresses complex challenges related to environmental issues. There are many parameters that can only be qualified and therefore incorporated into a smart environment. Using techniques provided by environmental analytical chemistry, if major variables such as cholesterol, city pollution, or food toxicity are to be determined, an effort should be made to develop places suitable producers. Higher low cost, small price, and low power consumption. In this sense, relevant contributions could be, for example, the use of smartphone cameras and photometric analysis, or the addition of pollution sensors to anti-pollution fitness masks. The field of wearable also offers a wide range of opportunities for these applications. In both cases, the usefulness of the obtained values were increased several-fold thanks to the incorporation of individual data, conveniently anonymized into cloud applications. For example, in this way runners could avoid the most polluted areas to the city. A growing demand also expected in a miniaturization of sensor and transceivers. Implementation of increasingly smaller devices will lead to a great amount of them in intelligent objects, thus offering opportunities for electronic music and sounds. Redundancy or interference rejection techniques, all of them will increase both reliability and durability of sensors. All in all, the future symbiosis between environmental analytical chemistry and ICTs opens up enormous prospects within the IoT and cloud system. There is scarcely any doubt that environment analytical chemistry, as well as many other disciplines, will fully benefit from important aforementioned advantages of cloud computing and IoT. Nevertheless, to date a detailed research in the literature has resulted in only a few relevant major contributions. Hence, the importance of the present work as a somewhat pioneering contribution in this application field. Fortunately, the future seems to be promising, although much work still needs to be carried out. For example, our research group is currently working on utilization of IoT for applications based on determination of anions and gotchas in water by means of self-development smart sensors. Declaration of competing interests. The author declared that they have now no competing financial interests or personal relationships that could have appeared to enhance the work reported in this paper. References. Okay, so we have finished with part reading. What I have understood about this is that They are created, okay, with the use of IoT, in this case, environmental analytical chemistry, towards a profitable symbiosis. It means that those applications with technology are going to increase, going to help, in this case, the huge advantage that it can have in the environment as an application and reducing the cost and collecting a big data, and it's going to be included in the cloud. Well, until that part we have finished with our reading. Okay, so thank you so